Okay, welcome back to the second half of the Comparators talk. All right, so in the second half, I'm going to move on to somewhat higher level constructs. And a lot of this is going to be about what we call the combinator methods on the comparator interface. And so one of the features that was added in Java 8 was the ability to add static methods and default methods to interface. And so in Java 8, the comparator methods sprouted a whole bunch of those. And so the idea is that these, what we call the combinator methods, are useful for constructing comparators out of lower level constructs. So if you can take some fundamental comparison operators and compose them to make comparators with more complex, interesting behavior. And so I've already, in the first half of the talk, I showed you some of the pitfalls you can run into even writing comparators that compare primitive values. And so you can run into many of the same problems when you get into more complicated comparators. So the combinator methods are really useful because it allows you to express complex behavior much more concisely than instead of writing out custom logic. So there are a bunch of them here. I'm not going to describe them right here, but basically we have this thing called comparing, which takes a key extractor and also will compare a int, long, and doubles. We have something called reverse that will take a comparator and return a comparator that's the reverse operation. There's something called then comparing, which will construct a two-level comparator for you. Nulls first and nulls last will provide special case treatment for nulls, and natural order and reverse order. So natural order is what I talked about earlier, which is a comparator that is implemented using the compare to method of the comparable interface, and reverse order is the reverse of the natural order. So what I'm going to do is I'm going to explain most of these in a series of demos. And the demo is going to use a very simple Java object, which I'm calling player. Imagine some kind of online game where you have a player who has a display name. Players might also have nickname, which might be null, and then an int value, which is the number of games played, and then a double value, which is a rating of some sort. All right, so I'm going to switch over to the demo here. All right, so basically I have often another file. I have something that generates a list of players. It's not really very important. It's just, there's really nothing interesting about the player object itself. And basically this method here, sort demo, takes a list of players and is responsible for sorting it. And then so my main method all the way down at the bottom just gets this list, shuffles it in a particular way, sorts it, and then prints it out. So if we run this without sorting, I'll just show you an example of the output. It prints a nicely formatted output here. So we have the display name, a nickname, the number of games played, and the player rating. And you know, there's just some made up names here and made up nicknames and a bunch of numbers. All right, so that's unsorted. And so let's set ourselves a little task here, which is sorting by the display name. And so I call this the long form. It's kind of funny because this is a Lambda expression. The long form that you had to use before Java 8 was you'd have to write an anonymous inner class. So you'd have to say new comparator, open brace, and so forth. Public int compare. And then you have to write this inside of it. So already this is shorter than it used to be. But basically, display name is a string, and a string is comparable. So we can compare one string to another. So the way to write a comparator for this, given two values A and B, we get the display name out of it and compare it to B's display name. So if we run that, we can see that this produces correct results here. And so if you look down the left-hand column, it looks like it's sorted in alphabetical order, and that works just fine. But we can do better than that, because notice there's this isn't very complex, but you can already see there's a little bit of duplication in here. The common thing that a comparator does when comparing two objects like this is get something out of the first object, get something out of the second object, and then compare them, either using the object's natural order or using another comparator that's been provided. So it turns out that there's a library routine that does that. It's called comparator.comparing, and it takes what we call a key extractor function. So I said, get something out of the first one, get something out of the second one. So that's a common routine. And so instead of you having to write that method call twice, what comparing does is it says, give me one function that tells me how to extract the value that you want to compare. I'll call it twice and then do the comparison for you. So that's what comparator.comparing does. Okay, so we run it again, and we get exactly the same results. So we get the names in alphabetical order. And what's nice is that we have static imports, so we don't even have to write comparator anymore. We just say player list.sort comparing players display name. And so that's kind of nice because it tells you exactly what's going on. And it's not much shorter than the Lambda expression up here, but I think it reads much better because it's more descriptive about what it's doing. I don't think I need to run this because it's basically the same thing as before. But here I'm going to do something different. So now the variation is player list.sort comparing player get display name, and then I call reversed after the end of it. And indeed, we can see the output is sorted in reverse order by the display name. So that's pretty neat. Okay, so there's another thing here, which is comparing int. So here we're calling get games played, which is an int value. And so instead of calling a comparator for this, if it has an int value, if you used objects, it would result in boxing and then using the natural order comparator of integer. So it's much more efficient if you say comparing int, because then it does the int comparison directly. So here we can sort by the number of games played. And so here you can see that by the number of games played, it's an ascending sort by the number of games played. So here's another one where we have a floating point number, which is the player's rating. And so again, it's comparing double. So we can extract a double value from each player object and then compare the double values directly as primitives. And in this case, what we're doing is we're reversing the comparator. So we will sort them from highest rating to lowest rating. So you can see the rating of this highest player, and then we have a descending sort down here. So I think you can start to see the flavor of these, which is that if you have some value that when you want to sort an object on, it's very easy to just really whip together a whole bunch of different comparators and use a key extractor method just by combining things in very simple ways. All right, now things are going to start to get a little bit more complicated. So the nickname, let's sort players by nickname. All right, what happens here? Ooh, looks like an exception stack trace, right? Null pointer exception. So what happened here was that, remember, I said the nickname is nullable. So what comparing does, the comparing method doesn't know any better. It says, we've handed it a key extractor method called getNickname. So it says, get the nickname from A, get the nickname from B, and then compare them using compare_to. Well, one of those is null, and so it's trying to invoke a method on a null value, which gives a null pointer exception. So we have to do something extra to deal with nulls. And so for this example, what I want to do is say, okay, let's just say nulls will be sorted first before any non-null value. So there's a thing in there in the library called, whoops. There's a method in the library called nulls first. So we'll wrap it in that. We'll wrap the comparator inside of nulls first. And we still get a null pointer exception. Why is this? So this is a little bit subtle here, because what we did was we put nulls first around the outside of this comparator that's comparing the nicknames. And that's actually the wrong thing. What this will do is, if we had a list that had actual nulls in it, then nulls first, the way it's written here, will sort those nulls first in the list, and then all of the players. And we don't want that. We want to deal with a null nickname. And so what we have to do is put nulls first inside. We have to do something a little special here, though, which is how we need to tell the sort algorithm how we are comparing that nickname in order to wrap nulls first around it to say, sort it this way, except treat nulls specially. So from the inside out, we're saying we take a natural order comparator. So that's in this case, the nickname is a string value, so we're using strings natural order. We're saying, oh, if it's null, sort those first. Otherwise, sort non-null string values in natural order. And the string comes from the nickname. Okay, and so here, that works now. And so we can see, we're looking at the report, the null nicknames are all at the top. And then we have a bunch of other nicknames sorted in alphabetical order. And so that's the result we want from this one. But notice here, there's a bunch of cases where people just didn't provide nicknames, so they're all null. And then most of these are, typical science fiction style nicknames. But everybody wants to be Spock, so a bunch of different people chose Spock. So let's say if we have duplicate nicknames, then we also want to within a set of duplicate nicknames, we want to do a further sort on the player's display name. So how can we do that? So that's where this new method called then comparing comes in. All right, so first let me show you the results to understand it. So if you look down this column here of the nicknames, nulls are still sorted at the top, and then Spocks are all here. But notice within the Spocks, these names are sorted alphabetically. If we go back up to the top where all the nulls are, the display names are also sorted alphabetically. So this is a two-level sort. So what we're saying is get the nickname and treating nulls specially by putting them first, sort nicknames in the natural order. And for nicknames that are equal, then compare the player's display name. So now there's a lot going on in there in 2 lines of code. So what I want to do is switch to an example of how somebody might write this incorrectly. All right, so in the bad old days, before we had the comparator combinator methods, you might have to write this out by hand. And I think on Twitter once I said I get all of my conference talks from Stack Overflow. Somebody posted this question. It's like, why doesn't this comparator work? I'm trying to sort nulls first. And well, it's because there's a bug in their comparator. And so this is what this is kind of, they used a different example, but this is basically what they did. I want to sort players by nickname, but the nickname might be null. So first thing I do is I do null checks. If the nickname of A is not null and the nickname of B is not null, then I'll compare them. Okay, so I compare nickname A to nickname B. And if they're different, then I just return that result. But if they're equal, then what I want to do is get the display names and compare those. Okay, that kind of makes sense, doesn't it? Well, there's this problem, which is, what do you do if one or both of the nicknames is null? Well, I think the guy didn't know what to do, so he just said, I guess I'll return 0 there. And the problem is that that doesn't work. Right? So if you run this, you get comparison method violates its general contract. And I'm not going to go through the details there, but if you look back at what this code does, if one of the arguments is null and another is non-null, it says they're equal. And that's clearly wrong because we want to sort the nulls first. So here's how you'd write this out correctly using kind of open logic without using the comparator combinator methods. And I'm not going to go through all the cases, but in order to write a method like this correctly, you really do have to go through all the cases. So if nickname A is null, if nickname B is null, then, okay, then I do my second level comparison. Oh, but if A is null and B is non-null, then A is less than B, so we'll return -1. Oh, okay, so if A is not null, right? Okay, so you can see when writing code like this, it's really easy to get something wrong. Like imagine if you had another piece of code that said, I want to sort these in reverse order instead. Well, you just switch the -1s and the switch the -1s and positive ones, right? And the code would look virtually identical, and you wouldn't be able to tell. You wouldn't be able to tell which is which unless you ticked through the logic very carefully or wrote a lot of comments to make sure that you were explaining it carefully. But the point here is that this whole what is this? This is about 20 lines of code or so. This is exactly equivalent to this 2 lines of code right up here at the top, which is what I showed in the original example. Comparator, well, it's similar to what I wrote in the original example. Comparator.comparing, get the nickname, sorting nulls first, then comparing the display name. So those 2 lines of code are it's kind of like a macro that expands to this 20-line comparator. All right. Okay. So let's say, all right, so I ran this one, the bad comparator, and I got the illegal argument exception. So what people often try to do is they'll say, oh, it's that new sorting algorithm that was introduced in Java 7. Why couldn't we just go back to the old sorting algorithm? And it turns out that you can. There's a property called Java util arrays use legacy merge sort. And so that uses the pre-Java 7 sorting algorithm. You set that to true. And so now we'll use the same bad comparator and look at what happens. Okay, remember, the task is to sort alphabetically by nickname with nulls sorted first. And so if we look here, well, null, Kodos, Merlin, Riker, Rogue, null, Draco, Hagrid, these aren't sorted at all. I mean, this is totally wrong. And if you look carefully, they're sort of sorted because between each null, there's a run of alphabetical names, and then there are a couple nulls, and then there's another run of alphabetical names, and so forth. But basically, this is totally the wrong result. So I cringe whenever I see somebody setting this property, use legacy merge sort, because it's shutting off the exception, but it also means they're probably getting the wrong result. So I strongly recommend that you avoid using the legacy merge sort. All right, so that's the good comparator. I don't think I need to show you that because it's the same as the previous one. Now here's a different variation. We're comparing by nickname with nulls last instead, and otherwise it's the same thing. So here we see that, now notice this is not reversed. This is sorting nulls last. So it's treating null specially, but it's treating it specially in a different way. So here we have the nicknames in alphabetical order, but the nulls all end up at the end. And so you do that by writing nulls last. And then I have one more variation here. Basically, so comparing and then comparing, if you just give them one argument, which is the key extractor, the extracted result must be comparable. And so my examples are using strings. And so strings are comparable, so that's all I needed to do. Sort by nickname or sort by display name. But what you can also do is pass what's called a downstream comparator. What I call a downstream comparator is once I've extracted the key, instead of calling compare to on the 2 extracted values, I can call a different comparator. And so if I wanted to, for instance, use a case insensitive sort or something like that, I could pass the case insensitive comparator. Or in this case, what I'm saying is I'll pass a downstream comparator, but instead of using the default ordering, which is the natural order, I'm going to pass reverse order. And so if we run this, this will sort the nicknames nulls last, but within duplicate records, it actually will sort by the display name in reverse order. So anyway, so this is just a flavor of all these different things. You can see in, I don't know how many examples here, 15 examples or something like that. This probably replaces pages of comparator code. So that's the real power of using these comparator combinator methods. All right, so there's some wrinkles here. There's sort of a strange overlap here in the APIs. So we've said the compare method returns a result which is indicating whether, given two objects, the result is less than, equal, or greater than. So if the result of a comparison method is 0, what's the relationship of that result to the equals method, object.equals? And so you might think, well, of course, those should be the same thing. If two objects are equal, then the compare function on them should always return 0, and vice versa. And so that's a nice property to have, to be clear, but it is only a nice property. It is not a requirement. And so we say if equals gives the same result as compare to equals 0, we say that the comparator is consistent with equals. But it is not a bug if a comparator is inconsistent with equals. Or I should say it's not necessarily a bug. All right, you might have written a bug because you didn't intend for it to be that way. But there are times when it is proper for a comparator to give results that are not consistent with equals. In particular, a comparator might result in, given two different values, might result in 0, saying that they are equal, at least in terms of the comparator. But if you call equals, that is object.equals on them, that might return false. So that's what we say is when a comparator is inconsistent with equals. And so there's an example of this in the JDK, big decimal. Big decimal has a scale, which is essentially the number of digits. And so 1.0 and 1.00 are not equals according to objects.equals. But if you compare them, they have equivalent values. So compare returns in 0. So there's some consequences for this. And so if you read the comparator specification, it says that if you have a comparator that is inconsistent with equals, a sorted set will behave strangely because it violates the general contract of set. And so an example of that is with tree set, which determines ordering and membership comparisons using a comparator instead of .equals, which is the general contract of set. So let me bring up some demonstrations here. I have a demonstration in JShell, which will so we can get through this pretty quick. Okay, so I'm going to use this half-up rounding mode a little later on. So let's say all right, so the easiest way to generate big decimals is to use a string. And so this is 1.000. So I'm going to generate two values here. So we say a dot compare to, here I'm using the natural ordering. 1.000 has the same value, compares equally to 1.0000. So numerically that makes perfect sense. If you say A equals B, the result is false. Ooh, that's kind of weird. Well, why is that? Well, the reason is it's very important that, it's potentially very important for big decimal to obey numeric consistency properties. So you might think that values that are equal will give the same result when the same operation is performed on them. And in fact, this is not the case, right? So if we say, let's create a new value 7 here. And so if we say 1.000 divided by 7 with a rounding mode of half up, that gives us 0.143. And if we divide 1.0000 by 7, we get 0.1429. And so clearly, these values are not equals to each other, but most importantly, these values are now numerically different. In one case, the first value is actually numerically larger than another. So anyway, so that's an important reason why something like big decimal, it's not, even though the comparison, the natural order comparator, or sorry, the natural order comparison for big decimal is not consistent with equals, this is one of the reasons that it isn't, because they really are different, because they have different scale factors that affect, that cause different results to occur given the same rounding mode. All right, so then there was that line about tree set behaving strangely. So let me create some sets here. Give a set of big decimal, create a hash set, and then create a tree set here. All right, so I'll create two sets, and then I'm going to add one of these numbers to the hash set and another one to the tree set. And so if we look at these sets, sorry, that's the wrong, I wanted to print out the hash set. So we have the hash set contains that one, and the tree set contains that one. All right, so let's compare the sets themselves for equality. So the tree set says that it is equal to the hash set. Okay, but what happens if we do the comparison in the opposite direction? Oh, boy, that's weird. All right, so what's going on here is that the way the equals set operation works is this wants to compare itself to something else. And so when what this object does is it iterates over the objects of the other set and then uses the equality comparison used by this object. And in tree set, it uses the comparator. So it's using the comparator to determine whether these values are equal, and if they all are, then the set is equal. And so as we saw earlier, the comparator says that 1.000 equals is equal to 1.0000. But the hash set does the opposite thing. It calls in the opposite order, it's getting values out of the tree set, but it's using dot equals to do the comparison. And what do you know? 1.0000 is not equal to 1.000 in terms of object.equals. So that's why the hash set says false and the tree set says true. So is this a bug? It's certainly counterintuitive behavior, but this is what the spec means when it says lost my place here. This is what it means when it says the sorted set will behave strangely, because you will get inconsistent results. So you have to be careful about this one. All right, so I did that demo. Basically, I don't know if I can. So basically, in Java 7, a new sorting algorithm was introduced that is more sensitive to correctness of comparators. And let me see if I can run through this in about 1 minute. I have to skip a bunch of stuff here, but basically, the heart of the timsort algorithm is it does merging of consecutive runs. And so here we have on the left an increasing run, and on the right we have another increasing run. And so when it wants to do a merge, it says, oh, the low end of the right run is greater than the lowest elements of the left run. So in fact, when the merge is done, those left 4 elements will stay in the same place. So you don't have to do those merging at all. And same at the high end. It says the highest ones on the high end of the right element, or about the right run, can be trimmed out of the merge. And so what happens is this establishes an invariant between the runs, which is that the high end of the left run must be greater than the high end of the right run. And if in the middle of the sorting algorithm, timsort detects under certain cases that that is not the case. That's the point where it decides to throw an exception. And it can only happen if the comparator has a bug in it. All right, so here's the summary. Use the library. Avoid writing custom comparison logic if possible. If you do write logic, you have to be very careful. Go through all the cases. Make sure you understand the rules. Otherwise, you might get an incorrect sorting result, or you might get the exception. Thank you very much.